Module 8.2, Second Derivative Applications. Objective 1, use first and second derivatives to solve optimization applications. Objective 2, use first and second derivatives to solve an area optimization application. And Objective 3, use concavity and inflection points to solve a real-world application. Objective 1, use first and second derivatives to solve an optimization application. Example 1. Of all numbers whose sum is 84, find the two with the maximum product. Well, let's say we have two numbers, x and y, and their sum is 84. So we have x plus y is equal to 84. And we're looking for the maximum product of these two numbers, x and y. Let's let m equal x times y, or the product of x and y. Okay, so if we're going to look for a product, let's go through and let's use our sum. In this case, let's solve for x. That x plus y is equal to 84. And we're going to subtract x from both sides. That would give us y is equal to 84 minus x. Okay? And this being the case, I'm now going to take this and substitute into our product problem. And so that's going to give us m is equal to x times, and then our equivalent for y, which was 84 minus x. And so m would be equal to 84x minus x squared. Let's find a critical value if there is one. And we're going to let m prime equal the derivative, which would be 84 minus 2x. And then we can set this equal to 0 to see if we can find the critical value. And so 84 minus 2x equals 0. Subtract 84 from both sides. And so negative 2x is equal to negative 84. And divide by negative 2 on both sides. X equals 42. Now, we need to remember that if we're looking for two numbers whose sum is 84, then our domain is going to be between 0 and 84. And let's talk about y. 1, if x is to be less than 0, then you would have a negative product, and that would not be helping you find the maximum product. If x was bigger than 84, then your y value would have to be negative in order for the sum to be 84. And if you have a positive and a negative, again, you'd have a negative product, which would not be maximum. So our domain's in the interval of 0 and 84. And we've got x is equal to 42. Let's take the second derivative of this. So if m prime was equal to 84 minus 2x, then m double prime is going to be equal to negative 2. And so what would the double prime, or the second derivative, at our x is equal to 42 going to be? All right? And it would still, since there's no x values in the double derivative, it would still be equal to negative 2, which means that this function is concave downward. Then if it's concave down, then this value is going to be a maximum point. So we have a max at x equals 42. And if our sum is got to be 84 and x is 42, then that means y will be equal to 42. And so 42 times 42 would be the maximum product. Example 2. How would you divide a 28-inch line so that the products of the two lengths is a maximum? X is the value of the first part. Then the rest of it, or 28 minus x, must be the value of the rest of the board. So we have x, and 28 minus x is the rest of the value. The products of these two lengths would be x times 28 minus x. We're going to let that be equal to m again, because we're going to try to find the maximum. So that would be 28x minus x squared is equal to the max to the m. And then we're going to find m prime, which would be equal to 28 minus 2x. And we're going to set that equal to 0 as we did in the last example. And we're going to get negative 2x is equal to negative 28, and so x would be equal to 14. Now let's talk about our domain for x again. X has to be between 0 and 28, and the reason being is it can't be less than 0 because you would not have any board at that point in time, or you would not have a link. And it can't be greater than 28 because then you would not have a other value, critical value at x equals 14. If m prime is equal to 28 minus 2x, let's try the double derivative. And that would give us is equal to negative 2. The double derivative at our x equals 14 is still going to be negative 2 because once again, this one doesn't have an x value for me to plug 14 in. And so our double derivative would be equal to negative 2, which would mean that this function is concave downward, and that at this value, this would be a maximum point. And if x is equal to 14, and we plug x equals 14 into the 28 minus x, that would be 28 minus 14, and so y would be equal to 14. And so 14 by 14 would be the lengths of the line that would cause the maximum product. Example, a carpenter is building a shed with a fixed perimeter of 40 feet. What are the dimensions of the largest shed that can be built? All right, so let's draw this shed. We need to remember that we've got length and width. And since we have a fixed perimeter of 40 feet, we know that 2 widths plus 2 lengths have to be equal to 40. And as far as area goes, area of the shed would have to be length times width. Take this perimeter equation and solve it for L. So that would be 2W plus 2L is equal to 40. Subtract 2 W's from both sides. That would give me 2L is equal to 40 minus 2W. Divide by 2 on both sides. And so L would be equal to 20 minus W. I'm now going to take this and I'm going to plug it back into my area formula. So that would be area is equal to length, which was 20 minus W, times width. And so my area would be equal to 20W minus W squared. And now that we've got area in terms of W, we're going to find the critical value of area. So we're after area prime, which is B equal to first derivative, which is this. And then we're going to set this equal to 0. And I'm going to subtract by 20 on both sides. So negative 2W is equal to negative 20. Divide by negative 2 on both sides. So W equals 10. Now remember, as far as our domain, we need to remember that any width or any length has to be between 0 and 20. Here's why. Obviously, you can't have a width of 0 or you'd have a infinitely thin shed. Okay? And if your length was 20, then you would have 20 here and 20 for the lengths, which would give you no width. We know that our lengths and our widths have to be between 0 and 20. Since we've got W is equal to 10, we can take the second derivative and find out if it's going to be a maximum or minimum point. See what this critical value is going to be. So remember that our area prime was equal to 20 minus 2W. So area double prime would be equal to negative 2. So if we take this value and plug it into our area double prime, it's still going to give us negative 2 because there was no x values for us to plug 10 into. So this tells us that this value is going to be concave downward and that this is going to be a maximum point. And so our dimensions of the largest shed that we can build is going to be a 10 by 10, which would give us 100 square feet. Objective 3. Use concavity and inflection points to solve real-world applications. Example, the concentration in milligrams per cc of a drug in a patient's bloodstream T hours after injection is modeled by this function. Use the x and y intercepts, first derivative and second derivative, to graph the function. Use the derivatives to find the intervals in which the concentration increases and decreases, and use the derivatives to find intervals of concavity and interpret this in the context of the problem. Okay, starting off part 1, let's go and find the x and y intercepts. So let's look for the x-intercepts first. And our x-intercepts, that's when y is equal to 0. Or in this case, when c of t is going to be equal to 0. So we'll have 0 is equal to 0.8 t e to the negative 0.45 t. And since these are already set up in factors, we can separate them and set each one of these equal to 0. So we've got e to the negative 0.45 t equal to 0. And we have 0.8 t is equal to 0. Now, there is no way that this can be equal to 0. However, in this one, 0.8, we can divide on both sides, and that would give us t is equal to 0. So, we have 0, 0 is going to be our value. So we've got t here and c of t there. Okay, very good. Alright, so we now have found that the origin is the x-intercept. And we pretty much know that if the origin is the x-intercept, then it's probably going to be the y-intercept. But let's take a look at it just nonetheless. So we're going to find the y-intercept, okay, which means we're going to let x equal 0. Or in this case, we're going to let t equal 0, okay? So, because t is our variable that we're dealing with. And so we're going to put 0 in there. So it'll be 0.8 times 0, e to the negative 0.045 to the 0 power if we put 0 in for t. And that will give me here, that'll give me 0e to the 0 power, which is 0 times 1, which is 0, which is what we thought. So we have the origin is also the y-intercept. In the second part of this problem, we are going to go through and we're going to find the derivative of c of t. So we need c prime of t. Now if you'll look at this function has two things multiplied together, so we're going to have to use the product rule. Alright, and write my little formula there. Okay, so u, which is 0.8t, times the derivative of v, which is e to the negative 0.45t, times the derivative of the inside, which is times negative 0.45, plus, and we've got u prime, which is 0.8 times v, which is e to the negative 0.45t. Okay? Now, we're going to go through and simplify this. And if we multiply the negative 0.45 with this, we should end up with negative 0.36 t e to the negative 0.45 t plus the 0.8 e to the negative 0.45 t. Okay, and we have now found the derivative. Because this function, this derivative, has exponentials and it is a polynomial, then there's nowhere greater than 0 that it should be discontinuous. So what we need to do is let this be equal to the 0. So we're going to say 0.36 t e to the negative 0.45 t plus 0.8 e to the negative 0.45 t is equal to 0. We're going to factor out e to the negative 0.45 t. And that would leave us with negative 0.36 t plus 0.8 and equal to 0. So we're going to separate them and let each part equal to 0. So we've got e to the
negative 0.45t equal to 0, and we've got negative 0.36t plus 8 equal to 0. Again, we know this can happen, so we're looking at this one to see if we can find a critical value. So we're going to subtract 8 on both sides. So negative 0.36t is equal to negative 0.8. We're going to divide both sides by negative 0.36t. And so that will give us t is equal to. So now I'm going to separate these two factors and set them equal to 0. Alright, and on this one, it can occur. On this one, I'm going to subtract 0.8 from both sides. So that gives me negative 0.36t is equal to negative 0.8, and I'm going to divide both sides by negative 0.36. And so that should give me t is equal to 2.2. So now we need to take a number line, and we need to set up our intervals, and we need to talk about this possible critical value, which is 2.2. Now remember, our first interval starts at 0 because that's when the drug is injected into the body. And then at that point in time, 2.2 is going to split region 1 and region 2. Okay, and now we're going to take a test point, and we're going to let's try 1. And we're going to put 1 into the derivative, and we're going to see what kind of value we're going to get. So in region 1, we're going to take e to the negative 0.45 times 1 times negative 0.36 times 1 plus 0.8. Okay, and if we look at this value right here, this is going to be a positive, and we're going to multiply that. And if you look at this value right here, we get negative 0.36 plus 8. That's going to be a positive right there. And so in this first interval, we've got a derivative, first derivative, that's going to be positive. Let's look at the second region. Okay, in our second region, we're going to take a point like 3. So that would be e to the negative 0.45 times 3. Okay, times negative 0.36 times 3 plus 0.8. Now if we look at this one, this is going to be positive, which will give us a negative value in the second one. So notice that we have a critical point at 2.2, and since the derivative is positive in the first one and the derivative is negative in the second one, then we know that we're going to at 2.2. So function that is going to reach its relative maximum at 2.2. We have an interval of increase of this function between 0 and 2.2. And then we have the function decreasing from 2.2 to infinity. So now let's take a look at this function, and we're now going to find the second derivative. Since we knew that the derivative of this function was equal to negative 0.36t e to the negative 0.45t plus 0.8 e to the negative 0.45t, then we'll be able to take the second derivative. And in this case, again, once again, we're going to be using the product rule, so it'd be negative 0.36t times the derivative of the second one, which is e to the negative 0.45t times negative 0.45 times negative 0.36 e to the negative 0.45t. Okay, so that's the first one. Plus, let's do the second one now. 0.8 e to the negative 0.45t times the derivative of the inside, which is negative 0.45. All right, we need to do a little simplifying here for c prime t. So that would be equal to, and we need to multiply these two things together. and that'll give us a positive 0.162 t e to the negative 0.45 t. And in the second part, we're just going to end up what we've got there. So that'll be minus 0.36 e to the negative 0.45 t. And then the last one, we're going to combine the 8 and the negative 0.45, which will give us negative 0.36 e to the negative 0.45 t. Okay, and notice that these two things right here are like terms. So that's going to give us C double prime of t is equal to 0.162 t e to the negative 0.45 t minus 0.72 e to the negative 0.45 t. Alright, so now I'm going to go ahead and factor out my e to the negative 0.45 t like we did earlier for the first derivative. So that's going to give me 0.162 t minus 0.72. And this is equal to 0 to find out where we might have an inflection point. Obviously, we're going to set the first one equal to 0, and we're going to set the second one equal to 0. And this one is a no-go. And this one, we're going to add 0.72 to both sides. And that gives me 0.162t is equal to 0.72. We'll divide by 0.162 on both sides. And so that will give me t would be equal to 4.4. We're going to go ahead and set up our number line. And we know that 0 is our starting point, and we know we have 4.4 here. And so we know we've got two regions that we're dealing with. Now, to make this problem just a hair easier, we know that no matter what we do, that e to the negative 0.45 t is always positive. So all we're going to concern ourselves with is this one, because in this one, if it's positive and it goes with the other positive, it's automatically positive. If this one is negative, then it goes with the other one, and that will give us a negative. So everything is dependent on the 0.162t minus the 0.72 is going to determine where the second derivative. Okay, and we are looking, let's go through and let's plug a number in for region 1. Let's say 2. So we're going to substitute 2 because it's a good test point in for t. So that'll be 0.162 times 2 minus 0.72. And this is going to give us a negative answer. So region 1 has a negative for the double derivative. All right, let's try a number in region 2. Let's try like 5. So that'd be negative 0.162 times 5 minus 0.72. And notice that this is going to give us a positive value. And so we have a positive. So notice that our double derivative changes values, and that 4.4, we're going to have an inflection point. At 4.4, okay, we are concave downward in the interval from 0 to 4.4, and we are concave upward in the interval from 4.4 to infinity. Let's talk about what we know. We know first that the x and the y intercepts are at the origin 0, 0. We know that we have a maximum point at 2.2. We know that this function increases between 0 and 2.2. We know that this function decreases from 2.2 to infinity. We know that we have an inflection point at 4.4. We know that it is concave downward between 0 and 4.4. And we know that this is concave upward from 4.4 all the way to infinity. We have concavity. We'll say our 4.4 is right in here somewhere. And here's our 2.2 right in here. So we're going to reach a maximum point here at 2.2. This function is going to start heading downward. Around 4.4, it's going to stop going down as fast, and it's going to start doing like that. Okay, so notice that this thing was heading down more and more all the way till it got to its inflection point, and then it started going down less and less. Still decreasing, but decreasing less and less. So it's almost like it let off the accelerator from there to the end. This is what we know. 1, because of the first derivative, because of C prime of t, we know that this drug is going to increase in the bloodstream from 0 hours to 2.2 hours. And then from 2.2 hours, it's going to decrease in the bloodstream from 2.2 to forever. Okay? It's going to continue to decrease the concentration of this drug in the bloodstream. We notice that, too, because of the double derivative in this case, and because of our inflection point, 4.4 hours, this means that once this drug started to decrease, it accelerated in decreasing up to 4.4 hours. At that point in time, the decreasing started to level off after 4.4 hours.